Right now, billions of water molecules are about to do something almost no other liquid on Earth can do. As temperature drops past zero, they lock into a crystal lattice so precise that no two structures have ever been documented as identical. This is the secret architecture of ice, a system so strange it breaks the basic rules of solids, shatters rock, and has been quietly recording Earth's climate for over 400,000 years. To understand ice, you have to understand water's strangest secret, the hydrogen bond. Each water molecule is a bent little magnet, one oxygen atom, two hydrogens, and a slight electrical imbalance that lets it grab onto four neighboring molecules at once. In liquid water, this network is chaotic, constantly breaking and reforming. But the moment temperature crosses freezing, those four-way handshakes lock into place. Each molecule settles into a fixed position, bonded to exactly four neighbors in a rigid, open lattice. The result is called hexagonal ice, Ice 1H. And that single word, hexagonal, explains almost everything you've ever noticed about frozen water. It's why snowflakes have 6 points. It's why ice cubes sometimes show faint six-sided facets. The molecular geometry forces six-fold symmetry onto the entire structure, scaling up from atoms you cannot see to crystals you can hold in your hand. And here's something we'll come back to. Even though every ice crystal obeys the same six-fold rule, scientists have never documented two snow crystals with truly identical branching patterns. Before any of that elegant geometry can form, water has to do something it actively resists: start. Pure water can be cooled well below 0 degrees Celsius, sometimes past -40, and still stay liquid, a state called supercooling. Molecules need a scaffold, a starting point to organize around, and in nature, that scaffold is rarely random. Dust particles, pollen, and even specific bacterial proteins act as ice nuclei, offering a surface whose spacing happens to match the geometry ice wants to form. Some bacteria are so good at this job that they're used industrially to trigger snowmaking. Without a nucleus, water droplets in clouds can remain liquid at astonishingly low temperatures, exactly why aircraft icing and supercooled rain are such unpredictable hazards. Once nucleation finally happens, the process accelerates. A single stable cluster of correctly bonded molecules acts like a seed crystal, and surrounding water molecules race to attach in the same six-fold pattern, layer by layer, building outward from that first invisible spark.
This is where ice stops being chemistry and starts becoming art. As a young crystal grows, its shape is dictated by two variables, temperature and humidity. A physicist named Ukichiro Nakaya spent decades growing snow crystals in a lab, mapping which conditions produced which shapes. Around -2 degrees Celsius, crystals form flat plates. Near -5, slender columns and needles appear. Closer to -15, the famous branching stars take shape, the classic snowflake silhouette. Each branch grows fastest at its corners because those points are more exposed to surrounding moisture, pulling in new molecules faster than the flatter faces beside them. That uneven growth is called dendritic branching. Corners grow faster, which makes them stick out more, which makes them grow even faster. As a crystal falls through a cloud, it passes through dozens of microclimates, each one nudging the branching pattern in a new direction. With millions of possible paths through the atmosphere, the odds of two crystals tracing an identical one are effectively zero. That's the real reason no two snowflakes match. Not magic, just an astronomically complex weather history written into solid form.
But here is where ice quietly breaks the rules every other solid obeys. For almost every substance, the solid form is denser than the liquid. Molecules pack tighter once they stop moving. Water does the opposite. Because the hydrogen-bonded lattice of hexagonal ice is so open and rigid, it takes up about 9% more space than the same mass of liquid water. Solid water is lighter than liquid water. That single anomaly is one of the most consequential facts in planetary science. It's why ice floats instead of sinking. If it didn't, lakes and oceans would freeze from the bottom up, killing nearly all aquatic life every winter, and most of Earth's oceans would likely still be frozen solid from the last ice age. It's also why a sealed bottle cracks in the freezer, why potholes form when water seeps into pavement and expands, and why frost can physically shatter solid rock through repeated freeze-thaw cycles, a process geologists call frost wedging.
And hexagonal ice is just the beginning. Under extreme pressure, deep inside glaciers, comets, or icy moons, water molecules can be forced into at least 17 different crystal structures, each with its own lattice geometry and density. Some are denser than liquid water. A few are predicted to exist inside the cores of giant icy planets like Neptune and Uranus. Cool water fast enough that molecules have no time to organize into any lattice molecule, and you get amorphous ice, a glassy, structurally disordered solid believed to be the most common form of ice in the universe, coating dust grains in interstellar clouds. And there's a stranger hybrid still, clathrate hydrates, cage-like ice lattices that trap small gas molecules like methane inside their crystal structure. Vast deposits of methane clathrate sit frozen along ocean floors and inside Arctic permafrost right now, holding an estimated amount of carbon greater than every coal, oil, and gas reserve on Earth combined.
That frozen cage is currently under threat. As global temperatures rise, Arctic permafrost and shallow ocean methane clathrates are warming, raising the risk of destabilizing those ice cages and releasing trapped methane, a greenhouse gas more than 80 times more potent than carbon dioxide over a 20-year span. Meanwhile, the floating sea ice we started this story with is disappearing in real time. Arctic sea ice doesn't just respond to warming, it accelerates it. White ice reflects most incoming sunlight back into space, but the darker open ocean left behind absorbs it instead. A feedback loop researchers call Arctic amplification. One reason the Arctic is warming nearly 4 times faster than the rest of the planet. The same 6-fold lattice that builds a snowflake on your sleeve is, at planetary scale, one of the most important thermostats Earth has ever had.
But ice isn't only fragile, it's one of the best record keepers on the planet. As snow compacts into glacial ice over thousands of years, it traps tiny bubbles of the atmosphere that existed the moment it froze. Drilling deep into Antarctic ice sheets, scientists have pulled cores containing an unbroken climate record stretching back over 400,000 years, preserving the exact temperature and greenhouse gas concentration of ancient atmospheres, bubble by bubble. Every layer is a page in Earth's diary, written not in ink, but in the same hexagonal lattice that built the last snowflake you ever caught on your tongue. The molecules don't know they're keeping history. They're just doing what hydrogen bonds have always done, locking into the only shape geometry allows them. Look closely next time it snows. What lands on your sleeve isn't random. It's frozen physics, frozen history, and frozen warning, all in one 6-pointed crystal. Remember,